Hi everyone. You've made it to week 4, so good for you. I hope you're finally, settling into a good routine and that the videos are helpful to you. This week, this is the only required activity. It's the only one we're covering this week. And this whole section is on linear regression. So you're going to spend a lot of the week playing around with the calculator, getting used to doing scatter plots and finding the best fit line or the line of best fit on the calculator. So just make sure you dedicate that time, even though we're only doing one section, to get comfortable using the calculator. So the whole goal in this section really is to be able to write the equation of the line, which we've done in previous sections. Back in a few sections before this, we took 2 points and found the equation of the line. But the idea that this is working off more like real data, where it's maybe the slope between each set of points is not exactly the same. So we don't really have one slope to go off. So what we do is we find the equation of the best fit line, and that's what we use the calculator for. So this first table right here is a table that shows the cost increasing for tuition as the years go by. So our input variable is the number of years past 1996. So 1996-97, that's kind of our starting point. That's what we're calling our 0. So the first thing we have to do is graph that. So just for sake of time, I did that ahead of time. And I plotted number of years on the x-axis, cost of tuition on the y, and I counted by ones on the x, and I counted by 1,000 on the y. So you might want to pause and make yourself a graph and then check it with mine, and then come back. Okay, so that graph, it actually looks pretty good. You're not going to find real life data that comes out much better than that. I mean, that looks like a perfectly increasing line. It could be a little off because of just my estimating some of those points, but we can definitely tell that's a pretty good line. So does there appear to be a linear relationship between the number of years since 1996-97 and the cost? Definitely. It definitely looks linear. Okay, so yes. This looks pretty linear. Okay, and as the years increase, what's the general trend? So I just mentioned that looks like an increasing line. So what's the general trend is as the years increase, or I'll say as years go by, the cost increases. So if this were perfectly linear, and I could find the slope between any two set of ordered pairs and it was exactly the same, well then I would go back to that point slope form that we did a few sections ago and write the equation. Okay, so just keep that in mind. We're really doing the same thing. It's just that this is not exactly linear. So the next thing, let's see, they're having us draw the best fit line. So I'll just take a minute and I'll just kind of draw the line that looks like I can go through most of the points. Okay, and now we're going to find that equation of that line. So here's where the calculator comes in. I am going to post a video that shows the steps for doing regression on the calculator. What the book is giving you right here is actually really good steps, and they show you each screen. You are going to have to do something, and again the video will help this, to go into your catalog and turn diagnostic on. And that's just going to make sure that you're going to get the correlation coefficient that we're going to use in a little bit. Okay, so what they're showing us first to do is to go into stat and then edit, and we're going to put our values into our list. So let me just kind of circle. This is where you're going to put all your x values, and then this is where you're going to put all your y values. Okay, it's going to give us the next thing we want to do. Okay, once I have my data in there, I'm going to do linear regression. So that's under stat calc. That's what they're telling you right there. Go down to 4, which is linear regression. And if you don't have any other lists in your table, you can just press enter. Sometimes we have to put, let me show you. Sometimes we have to put like an L1, L2 there. If I happen to have other lists of data in my calculator, I have to tell it which 2 lists I want to use. So at this point, they're giving us, you see y equals ax plus b right here. This is everything we need. Okay, they're using a for slope. They're just using a different variable, but b is still our y-intercept. Okay, so we're going to write our equation. So y is approximately, did I say how to round? 3 decimal places. Okay, so 915.943x plus 12,769.952. Now, this probably would actually make more sense to round to the nearest hundredths instead, because this is talking about money. Our y-intercept is this right here is the initial cost of tuition in that first year. So it really would make more sense to have that be 0.95, but we'll just kind of follow what they want. And this right here, let me just kind of draw, I don't know if they asked this later, they may, so I may be answering my questions kind of ahead of time. But our slope, this is the amount that the tuition increases each year. So again, that's money, so kind of would make more sense to round it the way money would be. But either way. So there's our equation of that line now. If we had done it by hand and found some of the slopes and used point slope, we would get something close to that. So now they're having us do the same thing with this equation, or having us fill in for all these outputs, 0, 2, 4, 6, 8, and filling it in for the predicted, meaning using our equation. So each one of these I'd plug 0, I would plug 0 into my equation for x, then 2, then 4, and so on. And so we're getting these values from our equation. And then if you kind of look back to that first page, it gives us a good idea of how good that line is. So if I look back to the data table, it said 0 maps to 12,994. So using my equation, I get 0 mapping to 12,770. So you can go through each one and see just how accurate our equation, our line of best fit or linear regression equation is. Okay, so 6 is going to use our equation to do something that's not actually a data value, a original input value. So they want us to now use it for t equals 3. So I'm going to plug in, or I had x I think I was using, but they were using t, but that's fine. 943 times 3 plus that 12,769.952. Okay, I kind of ran out of room here, but so when I end up getting this out, y comes out to be approximately 15,517.78. Okay, so that's dollars. So that is the cost 3 years past that 1996, 1997. So that's something we didn't have on our original table. So now our equation, we can use it for all different values for all different number of years rather than just the 6 that they gave us. So if we look at this paragraph right down here, what we did was we predicted if t was 3, t of 3 falls right here, right? In between there. So it falls within the input values that were on our original data. Okay, so that's what we're calling interpolation. Interpolation is when we use our equation to predict something that's within the range of our input data. Okay, extrapolation would be if I'm going to try to predict something outside of this. So let's say I want to know what happens 15 years past 1996, 1997. That would be considered extrapolation because it's outside my original input. So actually this is what we're, part B, they're having us do just that. So they're having us predict something that is outside. So this right here, that is 14 years past. So we're going to use 14 for there. And this we're going to use 19. So if you plug those in for t, let's see, for the first one, when t equals 14, you end up getting a cost, if you do the arithmetic, of $25,593.15. So that was in the year 2010, 2011. And then if t equals 19, you end up getting a cost of $30,172.87. So that's what we would call extrapolation, okay, because I predicted it outside what was originally given to me, okay? Which prediction do you believe to be more accurate? Well, the further out you go from our original data, the less we know what's really going to happen. So we would really say the 2010 to 2011 is probably a better prediction. Really just because, as we said, we wrote this equation for the data that we have, and that's only going to that 10 years past. So the further we get away from that original data, the less we really know what's happening. Slide, let's see what we've got here. Okay, so the next one, we're going to use our regression equation to figure out when the costs come out to be 25,000. So that is using our equation just in the opposite way. We're going to plug in 25,000 in for our output now, and then we're going to solve for a number of years. So our slope was 915.943. I'll put the t back in, plus 15,517.78. Okay, and when you get that, t comes out to be about, if you solve that for t and subtract over the y-intercept and divide out the slope, it comes out to be just about 13 years. Okay, so that's in the year 2009, to 2010. That would be the year that it would start to reach 25,000. Okay, so we're doing now this just really the same thing for another example, making a scatter plot. So I already kind of set up the graph, and let me just plot these points really quick. Okay, so this goes to a little over 400, 4 goes to 465, 8 goes to 492, 13 goes to 558. I'm kind of just doing this a little bit fast, so just bear with me. I'm going to skip to just that last one, just so I can get some more points on there. 775 is going to go up here. Whoops. So that's, my graph is obviously a little bit off here, because mine's not looking very linear. Okay, so I'm going to let you just kind of filling in that graph. If my video gets to be over a certain amount, I can't post it on YouTube, so it takes me a long time to graph those accurately. So I'm going to just skip over that a little bit. But I do want you to now practice finding your best fit regression. So if you go on the calculator and do the exact same steps, your regression equation for this one is going to be about y equals 13.10x plus 405.30, so 405.30. So what's the slope of this line? So it's easy to pick out from the equation, but let's figure out what it actually means. So my slope is about 13.1. Okay, so going back to this is year since 1977 and the number of degrees. Okay, so that really means that the number of degrees being awarded is rising a little over 13.1 per year. And use our regression model to predict the number of bachelor degrees that will be granted in the year 2010. So for 2010, we're talking about if that were 33 years past that original 1977. So if I use my equation, y equals, plug in 33 for x. Let me just add one more thing. They didn't ask about the y-intercept, but this y-intercept right here, that would be how many degrees were awarded in that original year. I mean, you can kind of look at it, this one versus the actual on the table came out to be 423. We got 405. So you can kind of see if you've got a good fit. Okay. And this comes out to be about the number of degrees awarded would be 837.6 0.6, and that's in thousands. Back up to the original, it says those number of degrees are in thousands. Okay, so the next slide, talking about how good is a good line. So these, especially the first one, we started to see that it was really almost perfectly linear. So it was a very strong correlation is what we're going to call it. So we have, I'm going to let you go through and read this page kind of thoroughly on your own, but we have this thing called a correlation, which we're using R for. And R ranges from -1 to 1. -1 would mean it has a very strong negative correlation, like this right here. This would be very strong negative correlation, this graph right here. Okay, and this graph right here, this would probably be what our correlation coefficient would be for that first one. This is a very strong positive correlation, okay, meaning it's an increasing line. So I want you to go through and read these paragraphs really well. So we start looking at R. You know, as closer we get R to 1, it means that my line is perfectly going through my data. So it's not, rarely will it be exactly 1, but a lot of times we get a 0.9. But as we start to get away from that, then it starts to get not, so right here, look at this example here. R is, we don't care that it's negative, but we care that it's getting further away from -1, because a -1 would be a nice perfect correlation. So as it's getting further away from that, think of it like this. You've got -1, you've got 0, and you've got 1. So over here is very strong, and over here is very strong. And as we start to move into the middle to that 0, we start to get more weak. Whereas our data does not look very linear anymore. Okay, so you can do this on the calculator. A lot of you may have already had, when you did your regression, you may have already seen R. If you don't see R, then you have to turn the diagnostic on. So like I said, I'm going to show you a video for that. And I think there's steps in the back of your book in Appendix C. What outlines that? Maybe further down. It's somewhere in this activity I saw that it tells you back in Appendix C, it shows you some more steps. So let's just do this one last thing together here. For each of the following, match the correlation coefficient with the corresponding scatter plot. So let's pick out the strongest correlation, okay? Again, don't care that they're positives or negatives. I more care about how close I am to 1 or -1. So my strongest correlation right here is A. Okay, A is the closest to 1. So if I look at my data, I would say the one that's closest to linear is this right here. Okay, and it's increasing, so I know it's got to be a positive R. So now between B and C, they're both pretty weak linear correlations. It's a matter of C is a little bit weaker, but sometimes that's hard to tell by the scatter plot. But at this point, you can just tell by R is negative on C, which means C needs to be matched with a decreasing line. So this would be our C, and this would be our B. This was going to be our weak, B would be our weak positive correlation, and C would be our weak negative. Okay, so I'm going to have you actually skip over this. I read through this part of the activity, and I'm not going to have you do that. Linear regression and looking at, so we're going to get rid of that. And these right here. And so actually I think I'm pretty much done with the activity. Let me just scroll up a little bit more. Yeah, we're not going to worry about these right here. Okay, I want you to just go through finding a regression line and making sure your calculator is giving you R out and knowing how to use R to figure out is your linear regression equation strong or not. Okay, 8 things right here to kind of recap the activity. Okay, you can cross off the things that I crossed off. And of course, you can always do any of these activities down here for practice. And all of these, the answers are in the back. So they're all just extra things to practice for in the back of the book. Okay, and of course, just let me know if you have any questions, and then look for that video if you're having any trouble with the linear regression on the calculator. Have a good day.